C. And what we have is again November 21. So a traveling wave on the surface of a lake has wavelength lambda, and 2 points along the wave oscillate with phase difference of pi. What is the smallest possible distance between these 2 points? So smallest possible distance between these 2 points means if we're pi out of phase, let's draw this. We essentially have right. Sorry, this is not a standing wave. We are talking about these 2 points being in antiphase, or pi out of phase means this is what we usually say, pi out of phase. And so they oscillate, they're completely oppositely, they're a half cycle out of phase, right? Because what we have is this would be a full cycle, that's our wavelength, but we have these 2 points. And so the smallest distance between these 2 points, smallest, that's pretty simple, right? We just saw that smallest possible distance would be this is lambda. Let me move this down, right? So if that's lambda, this is lambda by 2. And so half our wavelength is the shortest possible distance we're going to get for pi out of phase. Now we could also have 1 here, and that would be, this would be what? 3 over 2 lambda, right? And that's also pi out of phase. And so our answer is B, lambda over 2. That's the smallest possible difference. Now, this is polarization. No need to know that for the syllabus. Let's move on to question 13. The diagram shows an interference pattern observed on a screen in a double-slit experiment with monochromatic light of wavelength 600 nanometers. Screen is 1 meter from the slits, and we see this. Okay, what is the separation of the slits? Okay, so separation of the slits. So what we have is our formula. Separation over slits is B. And we have lambda, that's 900 times 10 to the negative 9. Distance from the screen is 1 meter. And then we have our fringe spacing. Now what we have to do is find out how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And both of these are halves, so I'm just going to count 10. It's not 11. So what we have is 1 centimeter, which is 1 times 10 to the negative 2, divided by 10. And so what we have is times 10 to the negative 3. And so what you get doing that is, and you can bring this up and make it 10 to the power of 3. Just use your calculator and you get 6 times 10 to the negative 4. And so our answer is D. That's our separation. And so on to question 14. String is fixed at both ends. P and Q are 2 particles on the string. First harmonic standing wave is formed in the string. What is correct about the motion of P and Q? Now these are both fixed ends, so what we have is our first harmonic would look something like, I think you guys know how to do this, but I'll just draw our diagram, right? So this is our node, which has 0 displacement. Node is equal to 0 displacement, and antinode is equal to max displacement. So what is it asking? What is correct about the motion of P and Q? Okay, P is at a node, yes, and Q is at an antinode, yes. So that's possible. Or Q, oh sorry, we're talking about first harmonic, then we would actually be like this, would it be? That is on me. First harmonic is like that. And so still my point stands, nodes and stuff, but this is not a node. This is an antinode, and or this is our node. Node equals 0, displacement max displacement. And so this is wrong. He is an antinode. Yes, Q is a node, that's wrong. P and Q oscillate with the same amplitude, that's wrong. They oscillate with the same frequency, that's true. So same frequency means they have the same time period. So although Q only goes about this far, while P goes all the way and oscillates between this max and this minima, they oscillate with the same frequency. So with the same time period, they always return to their equilibrium position at within the same time period. And so D is our answer. And why is a standing wave formed, right? Standing wave comes from two identical waves, right? Of same frequency and wavelength, right? Otherwise we can't have this superposition and interference, this perfect interference and superposition. So they need to be identical and traveling in opposite directions. And so that's how we need to have the same frequency at all points, because it's just two waves with the same frequency. And so on to, this is topic D. We can leave that for later. Hope this helped, and I'll see you guys in the next one. Please drop a like and subscribe if you learned something.